Okay, today you're going to be learning about describing functions by analyzing graphs. And we're going to watch a short video.
Splish splash, I was taking a bath. How does a graph represent taking a bath? In this lesson, you will learn to describe function relationships by analyzing a graph. Remember that in a function, each input goes to exactly one output. One of the most critical and challenging parts of reading a graph is interpreting the output. You should be able to identify the input and the output for a point on the graph. When the input is 2, the output is 6. This is the point 2, 6. But what does that mean? It is meaningless without using the labels to interpret. Now we know the input is time and the output is records sold. We can interpret this to mean after 2 months, 6,000 records were sold. Can you interpret the second point? An output of 12 means that after 5 months, 12,000 records were sold. We can tell a story about a graph by interpreting these outputs. When you take a bath, the water level slowly rises as you fill up the tub. Then it stays steady until you're ready to jump in, when it gets really full fast. It stays at the same level while you're in the tub, then it drops quickly when you get out. Finally, it slowly drains back to empty. This graph represents that process. Watch what happens to the output of water level as the input of time passes. First, the water level is slowly rising as the tub fills up. The output goes up. From 4 to 6 minutes, the water level is in one place. This is after the tub is full before you climb in. At 6 minutes, you hop in and the tub gets full really fast. Watch how high the output went. From 8 to 12 minutes, you're in the tub and the water level stays the same. Then you get out and the water level goes down fast. From 14 to 18 minutes, the tub slowly drains back to empty. An output of 0 means the water level is 0. The tub is empty. Let's look at another situation. A common misunderstanding is that because these graphs look identical, they mean the same thing. But the graph on the left tells the story of distance as time passes. And the graph on the right tells the story of speed as time passes. Interpreting what the output means can tell a completely different story. Let's take a closer look and tell the story of the graph of distance. I'm going to use a treasure map to illustrate the graph. The distance is how far Sarah is from the X. The graph will tell us as time passes the distance Sarah is from the treasure. She starts at a high distance from the treasure. For the first part of the graph, Sarah's distance from the treasure is decreasing. She is getting closer. The next section of the graph, the output stays the same. She's not getting closer or farther. She's probably deciding what direction to go. In the next section, if we look at the graph, the distance is increasing. This means that she's getting farther away. Wait, why is she getting farther away? Oh yeah, she had to go around the lake. Finally, her distance decreases until it reaches 0. A distance of 0 means she made it to the treasure. Now, let's see how different the story of speed is. As time passes, what does the output mean? Pause the video for a moment and see if you can tell a story about a race car driver using this graph. The starting place has a very high speed. This means that when the driver crosses the lap line, he's going very fast. But because he is getting close to a corner, his speed is decreasing, meaning he is slowing down for the corner. Then around the corner, he keeps the same speed. A flat line here doesn't mean that the race car driver stopped. It means he's going the same speed around the corner. After he passes the corner, he speeds up or his output increases to the finish line. And once he finishes, he slows down to a speed of 0, where he stops. In this lesson, you have learned to describe function relationships by analyzing a graph.
So let's take a look at some of these. In this example, it talks about a student walking and taking a bus to get from school to home each day. The graph to the right, labeled a commute home, shows the student's commute. It relates the time the student spends commuting and the distance he travels. Describe what the graph shows by labeling each part. So the very low steepness parts are when he is walking, because the distance will be increasing slowly. When it is flat, he is waiting for the bus. When it is steep, he is taking the bus because the distance increases quickly. And then that other less steep area is walking again. So let's try to do a day's commute for the quick check. The graph at the right shows a trip from home to school and back. The trip involves walking and getting a ride from a neighbor. Copy the graph and label each section. So, if we were to highlight the graph, we could talk about this step right here as walking, okay? The flat part right there would be waiting for the ride. Okay, so waiting. So time has passed, but you haven't gone anywhere. The steep area right here this area right here would indicate your ride to school, where the steepness would indicate an increase of distance from home pretty rapidly. This flat line is when you are at school. The downhill is when you're riding in a car on your way home. Okay. The flat line is getting out of the car. And the not so steep part right here is just like the other one, where you are walking. So if you turn the page, let's do some multiple choice ones here. Let's relate the graph to the situation. Suppose you pour water into a container at a steady rate. Which graph shows the change in the height of the liquid in the container over time? Now, realizing that the container gets wider from the bottom to the top, the correct answer would be A. Okay, right here. The rate that the water rises decreases steadily because the container gets wider at the top. So you have to think about that. So the graph at the right shows the time and distance of a moving object. Which of the following situations could be described by the graph? Could it be A, that a car is traveling at a steady speed? Or, I'm sorry, that's F. G, that a cyclist slows down as he rides up a hill and speeds up as she pedals over the top. H, a train slows down as it arrives at the station. And J, a plane accelerates steadily down the runway until it takes off. Now, one thing to pay in mind and keep close attention to is what the graph is telling us. So we're looking at time and distance, and this straight line is telling us F, that the car travels at a steady speed. Okay, so not any of these, not G, not H, and not J. All right, let's try labeling some sections. So in the first graph, you're exercising, and your heart rate is being compared to the change in time. So this first increase right here is an increase in heart rate. This part right here is a level, okay? And then this whole loop section, as it goes up really quick, it gets to the top of the peak. That is a very quick or jump in your heart rate. So a quick increase, and then it slows down. Okay, that little this little curved section could be like an interval sprint or something like that. Then again, it levels off, so you're maintaining then the heart rate. Looking at your checking account balance across time. So this is where it starts, your balance does. When it increases at this point, you've made a deposit. When it decreases, you've paid a bill or wrote a check. When it increases, it means deposit. You've added money. So let's look at the weekend temperatures. So I'd say the weekend starts right here on a Friday night. Okay. It warms up, the temperature increases, so it is warming. And this peak would be Saturday morning. Then the temperature drops or it cools for Saturday night. When it goes up, we would describe that as warming or increasing. Okay, and this would be like Sunday afternoon, right? Again, it's cooling down. Look at your hair length over time. The increases is when your hair is growing. So it is growing, and the decreases right here would be when you get your hair cut. So growing on the increase, cut on the decrease. So for example 3, practicing that, you turn on your oven to bake a casserole. Which graph best represents the oven temperature over time? Do you think that the temperature heats up and stays the same? Does it increase, stay the same, and then decrease? Or does it increase steadily and then alternates between cooling and warming during the cooking cycle? If you chose C, oops, it's going to change the slide. Let's go back. If you chose C, you were correct. This is more accurate to what happens in your stove. It's going to be too hard for it to maintain that temperature, so what will happen is it'll reach the temperature, it'll kind of kick off, and then as it starts to cool down a little bit, it'll ignite it to turn back on again and heat up. So there's a temperature gauge in there that'll allow that to happen. So looking at the multiple choice, which graph best represents a person's height from birth until age 80? Is it A, B, C, or D? And the correct answer is C. They grow and grow and grow, maintain relatively the same, but as you age, you start to shrink as your spinal cord compresses. So, inline skating. Describe what the graph at the right shows about a student's inline skating experience. Label each section. So the increase here would be showing them speeding up. This would be us cruising at a steady speed. Right here, they are speeding up. This going all the way down to 0 speed looks like they might have had a crash or an accident, and then they start again. They cruise again, but now they're at a slower speed. Here they're decreasing until finally they stop. Describe the relationship between the two quantities. So looking at the number of customers over time, the number of customers, you could say number of customers increase at a constant rate then decrease at a constant rate. So whenever the slope appears to be the same for any given part of the line, it would be considered a constant. What about the hiker in number 2? We're talking about altitude over time. So the height increases pretty quickly, then slower, and then quickly again. So height increases quickly, then slower, then quickly again. How about your postage stamp for the number of ounces and the cost? The cost of postage usually follows this pattern. The cost remains constant, as noted by the dashed line, remains constant. Then it jumps over and over. Okay. How about the water level? The height of the water decreases at a constant rate, remains the same, decreases, stays the same, and decreases. So, decreases, same, decreases, same, and decreases. You're texting a friend at a constant rate. You send the message, then you wait for a response. Once you receive a response, you begin texting a reply at a constant rate. So remember that constant rate is going to be a slope that is the same. So you want to label your graph as time and your speed of texting. So constant rate, remain the same, constant rate. Okay? If you cut your fingernails, then let them grow back, then cut them again. So in this graph, you will have time. And if you notice something or a pattern, we always put time on the x-axis. Remember, we've talked about those independent and dependent variables. Time is always independent. Usually, what goes on the y-axis, the dependent, depends on time, okay? So I'm going to let them grow back and then cut our nails. We're not going to work with a partner, but we will discuss these together. How are the graphs similar, right? The graphs represent the heights of a rocket and a weather balloon after they have launched. So you have the height above ground for graph A and the height above ground for graph B. So how are the graphs similar? How are they different? Well, the way that they're similar is they are both increasing. Okay? A is not a constant rate of change because it's not a straight line. B is a constant rate. Compare the steepness. Well, B is steeper, which means it has a higher or greater slope at first. Then A is steeper later. Which graph do you think represents the height of a rocket? That would probably be B because it steadily increases, not suddenly. So it's not a sudden increase. These graphs represent speeds of two cars. One car is approaching a stop sign. The other car is approaching a yield. How are they similar? How are they different? Well, both are decreasing A is decreasing quicker. But it doesn't stop. B is decreasing at a constant speed, and comes to a complete stop, as indicated at the point when it reaches zero speed. So which one represents the car approaching the stop sign? Oops, part B. Compare the steepness of each graph. A is steeper at first, and B is steeper later because it maintains that constant rate. The car approaching the stop sign would be B because it stops.